Wonderful. So then it's my pleasure to introduce our speaker today, who is Aadirupa Saha. Aadirupa is a postdoc at Microsoft Research in New York City. Before that, she did her PhD at the Indian Institute of Science in Bangalore, advised by Aditya Gopalan and Chiranjeev Bhattacharya. And she did a bunch of internships at really amazing places like MSR in Bangalore, INRIA in Paris, and Google AI in Mountain And she's interested in a bunch of topics that we all love here in Bandit, reinforcement learning, online learning. And she did a bunch of amazing work on all of these topics, mostly on partial monitoring, dueling bandits, which is a nice and exotic topic that we still haven't heard about here in these seminars. So I guess it was high time that we hear about this, especially on this new exciting work on contextual dueling bandits. Okay, so I'm going to pass it over to Aadirupa. Thank you very much for accepting our invitation.
Thanks a lot, Garge, Chiara, Chaba, everyone for joining. So I'm really excited to talk about this work because more than me discussing about the results, I'm really eager to hear about the feedback, questions, criticism. So please feel free to stop me wherever required. So before, without delaying much, let me start with the work. So the work is mostly on efficient and optimal algorithm for designing contextual dueling bandits. And this is a joint work with my amazing colleague, Akshay, who also at Microsoft Research, New York City. And this work was accepted in Algorithm Learning Theory 2022. So I'll not spend too much time on the problem motivation for this audience, just a few slides, few words for it. The problem of dueling bandit is generally often studied to understand and exploit the efficacy and usefulness of relative feedback over absolute ones, because oftentimes studies have shown that human beings are much more less biased, much more comfortable eliciting feedback in terms of in a relative scale or in terms of comparisons rather than in absolute values. For example, in a movie recommender system, we can often ask the users or the viewers that can you please, if we ask them to rate a movie in a scale of 0 to 10, oftentimes it suffers from user non-response or there's a lot of bias in terms of the scaling. But if we just show them a bunch of movies, 2 movies or couple of 3-4 movies and ask them to, can you please rank them according to your preference, or just let me know which is your favorite movie, oftentimes the feedback turns out to be much more consistent. So it's on a relative scale that we are collecting the feedback, and we want to understand how rich this feedback is, how far we can exploit it to do better predictions, to design better learning models. So that's the overall problem motivation. And this learning from relative choices has like enormous applications in various real world world applications. For example, movie recommendation we already talked about, but also like recommending items in any recommender systems, online shopping on retail chain management, recommending routes in Google Maps, or even when we go to the ophthalmologist, they ask us to, they try to understand which lens suits our eyesight best, asking us questions on a relative scale. So that's more or less the objective, to build efficient prediction models through relative feedback or through relative preferences or rankings instead of asking absolute reward feedback. So that was the famous formulation, which was basically why it was the problem of dueling bandit was famously proposed sometime back in 2009 from a group of researchers from Cornell University, which I believe is the first, who were the first to come up with this formulation for some information retrieval task. And since then, the problem has gotten a fair bit of attention in the learning theory community, at least in the bandits community, and famously studied as dueling bandit. So let's go a little more into the detail of how the exact problem formulation is. So it's kind of like, it's exactly like multi-arm bandit, but instead of, when in multi-arm bandit we query an arm, or we select an arm and we get to see the reward of the arm or some noisy random reward associated to the arm. Here we can query two items, or more generally a bunch of items, and as feedback what we get to see is a relative preference or some ranking feedback. For example, if we have k items in our decision space, and these k items can be thought of as like k movies we have in the movie hub, or k items to recommend whatever the number of items we are interested in, which we want to make predictions on. So at every round, so this is a sequential game, so at every round the learner can query two items, so maybe item 1 and 4 or whatever two items the learner can query, and it gets to see a noisy comparison feedback, OT. So OT is basically just an indicator of whether the left arm is better, whether the whoever is the feedback provider, they say the left arm is better over the right arm or the other way around. So we can use any convention. For example, if OT is equal to 0, we say that the left arm is better. If OT equal to 1, the right arm is better. And that is the only 0, 1 beat feedback we get to see with this sequential query. So what we can assume generally is that this OT, this preference feedback, is often getting generated from some underlying preference matrix, where every entry of this preference matrix is just an indicator of a relative strength of item I over j. For example, let me see if my marker works here. So suppose just take, for example, the row number 2 and column number 5. So this entry 0.61 is just an indicator of what is the relative strength of item 2 over 5. So we can assume that if there is an underlying preference matrix, which is definitely not known to the learner, but whenever the learner is querying item 2 and 5, they're getting to see a feedback, which is just a Bernoulli draw from a Bernoulli coin with bias 0.61. So there is a higher chance that higher probability 2 would win over 5. And that's how the feedback could be generated. This P could be a fixed thing. This P could be changing over time. The P could very much depend on the user context, whoever is providing the feedback. We'll come into those details later. So given this is the overall problem formulation, of course, we don't know what the underlying preference matrix look like. The learner need to understand at least some bit of the preference matrix, or at least gauge some bit of how the structure of the preference matrix look like, because ultimately the goal is to, assuming that there are some set of good items or nice items in the hindsight, the learner wants to figure out that good item as quickly as possible. For example, one concept of a good item could be, in this preference matrix, if we look at the first row, we can see that consistently all the entries are greater than 0.5. And in a preference matrix, because it has to be like all the entries has to be a bias of a Bernoulli random variable, these are in 0, 1, and always the diagonals are 0.5, and it's kind of like Pij is 1 minus Pji. So always that thing, because like the probability with which I is preferred over j is 1 minus probability j is preferred over I. So those are the only two constraints we have on the preference matrix, that it is in 0, 1, and is kind of this anti-symmetric structure. And we can see this preference matrix, the first row is consistently greater than 0.5, which means that on an expectation, if we make this item 1 randomly battle or randomly compared with any other item, the chances are 1 is going to be the winner on an expectation. So this is called the Condorcet winner. So one objective could be that without knowing this preference matrix, if we sequentially query this duels many number of times, can we find this Condorcet winner quickly enough? One famous formulation of how to measure the performance of a learning algorithm is oftentimes that we say that if the learner is playing two arms, xt and yt, let's try to figure out the relative strength of the item xt and yt with respect to the best item. So for example, pi star xt, so I star here is basically the Condorcet winner, whatever arm we are interested in. So pi star xt is just the relative strength of item I star over xt. And similarly, pi star yt is the relative strength of item I star over yt. And this minus half is just to make sure that when we are actually querying I star, so when xt and yt both are I star, then we are getting a 0 regret. So because pi star is half. So that's why this minus half, this is not really very important. So that's how the regret definition looks like. So that's how we define generally a famous formulation of dueling bandit regret is kind of this way. And we take the average performance of both the arms, we divide it by 2, and that's basically the instantaneous regret, sum it over all t rounds, that becomes the total cumulative regret over t rounds. And now coming to the one of the key observation here about the structure of this preference matrix is that I mentioned that all the preference matrix, the entries are in 0, 1, and we always have the structure that Pij for any ij should be equal to 1 minus Pji. And that's also the reason why we have all the diagonals equal to 0.5. So if we make a simple transformation, for example, if we just make this transformation p tilde, which is 2p minus 1, we compute another preference matrix p tilde, which now is all the entries are in minus 1 to 1. And if you note that because of this particular property, now we have this to be like an antisymmetric kind of matrix where, this becomes basically a zero-sum matrix. So any dueling bandit preference matrix can be seen as a zero-sum matrix and a zero-sum, like a zero-sum game between two players, the left player and the right player. And that's one of the observation. That's not our observation, that it is already known in the literature, but we are going to use it crucially in some of our algorithms. So that's just a view of dueling bandits as a zero-sum game between two players. And as I was mentioning, this particular regret objective that I flashed in the earlier slide with respect to some fixed arm I star and for some fixed preference matrix, this objective has been studied in dueling bandits throughout almost last 10 decades, more than 10 decades, with trying to give different kind of regret guarantees, changing the definition of I star, or changing the definition of regret a bit. But what was certainly some of the major crucial gaps in the understanding was where there were not too many work was what happens if this preference matrix P is not fixed. It is obviously the case that all the users who are giving the feedback are not going to generate the preferences from the same preference matrix. They should be a function of their user context. The preferences, like my preferences about a movie, is definitely not going to be same as my friend's preference. So the preference should depend on user context, and not only that, is this I star a Condorcet winner? Should it be fixed? Is it a good benchmark to compare against, or can we have better benchmarks? Can we actually compare or evaluate the performance of the learning algorithm against a stronger opponent, which make more sense? Maybe there is no Condorcet winner for some preference matrix, or if the preference matrix is changing over time, what is the notion of Condorcet winner? What are we going to compare against? So definitely the concept of benchmark was not very clear. The stationary preference matrices was, the assumption of the preference matrix is stationary, not changing with the users or time, is a bit unrealistic. And again, user-specific contextualization, which was needed to formulate these preferences.
Aadirupa, can I ask some clarification questions?
Yes.
So the regret definition on this slide is different than the regret definition that we saw in the other slide. There is a difference of constant, I don't know, 1/2.
No. I see. Because I should have mentioned it, that I already changed this definition to the zero-sum game. So now if you, okay, I think what you're talking about, this minus half.
The next was, yeah.
And if I now considering this P tilde to be my preference matrix and writing my regret objective with respect to P tilde, then the minus half doesn't show up. That's the only reason
it was not written with P tilde.
Yes, but I should have mentioned that. Yes.
I see. Okay. Do you want to say a few words about what's the motivation behind this regret definition?
Yeah, so this is firstly not our regret. This is the regret definition.
But before we study,
obviously,
I
yes.
want to understand why.
For sure. So I would say that basically consider that suppose there is a Condorcet winner, so there is kind of suppose we are trying to predict recommend movies to our users. And suppose all the users are coming from the same population distribution, so all the users are kind of very much same in their head, so they all have the same preference matrix inside their brain. And all the users like movie A, movies. So there is some movie A, and this movie A is like, if they recommend this movie, if we recommend movie A to the user, it's highly likely that they are going to watch the movie, or the more chances are more that they're going to prefer that movie over any other movie. So what we are trying to figure out, this movie recommender system trying to figure out, is how quickly we can converge to this movie. So say I star, whatever this A movie is, it is I star. So if
yeah, the interface is kind of weird a bit, right? Because we're gonna show two movies to the user. So we want at least one of the movies to be good, or like
that's true. That's true. I mean, so this is like this is called the averaged dueling bandit regret. But I would say that there has been like weaker dueling bandit regret has also been studied. That instead of like making XT white, so here in this case, if we want to achieve like a sublinear regret, eventually we want both XT and YT to converge to I star. But we can actually make it min over XT YT instead of like taking an average. And that's also fine. So that problem has also been studied. It is called weak dueling bandit regret. And we can put like, say, X belongs to min over XTYT, and then we just compare our definition with respect to this, and then sum it over all T rounds. That's also fine. I'm sorry about that. I'm just not able to write very well. But,
but in a sense, this is viewed as an online recommendation problem where we are most happy. If we didn't have to learn, then we would want to show both for XT and YT just the best movie or whatnot.
Exactly, right? Exactly. I mean, you can think it like as if we are very, very sure that this is the movie that you would like to watch. I mean, recommending something which is like I star is same as recommending just one movie I star. Because even if you're showing the two same movies twice, you are not getting any feedback. Because as a learner, I already know the diagonal is 0.5. So whenever we are saying like I star is being played, you can think like realistically as if we are just playing one arm, because we are so sure that this is the best arm. But if you actually want to collect any sort of feedback, then you have to query two distinct arms. So initially you have to query distinct arms.
Okay. Thank you.
Yeah. Okay. Thanks.
The underlying assumption, though, was that there is a Condorcet winner.
Here I'm saying here's a Condorcet winner, but this need not be a Condorcet winner. You can have any favorite item of your choice. It can be Condorcet winner or Boda winner or Copland winner. There are other sorts.
Definition is like regret against any item.
Any fixed benchmark. So we'll say this to be like a fixed benchmark regret. Fixed benchmark regret.
I see.
Okay. So the first question we will probably start addressing is that is this fixed benchmark regret, as already like we have some discussions, is it like a very good notion of regret, or can we make it somewhat bit stronger actually and have the learner get the learner being compared with a stronger opponent? So for example, instead of I star, so we were putting this max over I star, so that's also okay. I can just say that I am always comparing myself with respect to a fixed benchmark I star, and let's take maximum. So whatever sequence of XTYT I'm playing, let's fix that sequence and let's try to figure out the opponent which is like maximally beating my sequence of choices. So I'm just taking a max over I star, but it's still a fixed benchmark regret. This is still not Condorcet winner regret, but this is a fixed benchmark regret against a fixed best opponent. Now let me put this max inside. What does that mean? That now this I star was just this I star was a function of the entire sequence of XTYT that I have played over this T rounds. But now I am making this when I'm taking this max inside, this becomes IT star, because what I'm trying to say is like you play ITJT, or the learner plays XTYT, and I compare myself, like the learner is being compared with respect to the strongest opponent at that round. So that is much more stronger than the fixed benchmark or the standard regret that I have written here. So this we call the best response regrets, because this is like the best response or the best benchmark per round. Now, there might be like already some some of you might have noticed that this regret in general is not possible. I mean, very much same as multi-arm bandits. We can't just arbitrarily compare with respect to the if it has adversarial rewards, we can't just compare with respect to the best arm at every round. Similarly, here we can say that if we are not randomizing over XTYT, I mean, we can come up with such preference matrices or such dueling preference relations so that if XTYT is fixed and we are choosing the best response at every round, no matter what you play, we can always make you suffer a linear regret. How is that? Because it's considered this rock, paper, scissor kind of preference relation. Here, if we see, this is kind of, so always the learner has to play two arms, right? To understand anything, to fetch any information, or to gather any information, learner has to play two distinct arms. So suppose the learner is playing XTYT as 1, 2. Then my adversary's best response would be I, because then 2 is getting beaten by 1 with a margin of with 1. So the probability, so it will incur a regret of half. Again, if the learner plays 2, 3, the best response would be 2. And the learner gets a regret of half again. Again, it plays 3, 1, it gets a regret of half again. So I always can construct my best response. Looking at learner's choices, I can always come up with the best response and always make you suffer a constant regret every round. So obviously, if the learner is not randomizing and the fixed benchmark opponent is not oblivious to this randomization, we have no hope. So let's put this max outside this expectation and let us allow the learner to randomize over these choices of XTYT. So that's always the best response. So this is the best response regret we'll be working with, because otherwise we see that it's anyways hopeless. So now comes the point that even then, how do we come up with this PT? How do we come up with this randomization choices of the learner so that we can hope to achieve some sublinear regret guarantee here? So, I mean, before going to the algorithm, it seems like if it is a zero-sum game and so FT is basically now like the preference matrix here. So I should have just used here P instead of FT. I can just change it. So FT is just a preference matrix. Okay. This is just a preference matrix, and it seems like preference matrix is a zero-sum game. So what if we just play according to the Nash equilibrium? So suppose if XT and YT both are being played from the Nash equilibrium distribution of this zero-sum game, do we actually get a sublinear regret? Because we know by the definition of Nash equilibrium of a zero-sum matrix or zero-sum game is that no player gets a benefit of unilaterally deviating, and it seems like it's a game between the adversary and the learner. So if the learner plays from the Nash equilibrium distribution, can the opponent or the benchmark choose some better arm to make it suffer some constant regret? So that was the overall idea, how we try to come up with the optimal regret algorithm for this fixed benchmark notion of regret. So we exactly could not we don't know what the Nash equilibrium of P is, because we don't know P. So we have to be a bit more optimistic here. So what we can do is we can try to estimate P instead of because we don't know P, we can estimate it by randomly querying 2 pair of arms and try to estimate the Pij entries. So this algorithm looks a bit it is a very simple algorithm. So if I just divide it into a few steps, what this algorithm is trying to do is it's just trying to estimate this Pij entries over Ij pairs, all Ij pairs of arms. And I'm assuming that I have K arm here. I have a finitely many number of arms. So I'm just trying to estimate I can initially start playing randomly. I see I wins over J. I put okay, so then Pij equal to 1, and then I can accordingly keep on updating the empirical pairwise preference estimation. I can come up with my estimate of P tilde. And in fact, then what I can do is I can compute even an upper confidence bound of the pairwise preferences. So that I call the Uij matrix. So by this definition, this upper confidence matrix, this upper and lower confidence. So Pij with highly likely is going to be contained within the upper and lower confidence intervals of Uij. Okay, so let me not confuse anyone. So what I'm trying to say is this: we are just like trying to estimate the Pij matrix, with P hat ij. This is by empirical pairwise comparisons. And we are trying to estimate an upper confidence bound on this Pij. So always we can say that the actual pairwise probabilities are upper bounded by this upper confidence bound interval. And the main algorithm is basically how do we come up with this PT? How do we randomize the learner's choices? For that, what we say is we have this U matrix now, which is the optimistic estimation of the actual underlying preference matrix. Let's try to figure out, the Uij is not a zero-sum matrix, by the way. So we can't compute the Nash equilibrium of it, but we can compute as a coarse correlated equilibrium of this matrix. And this is some concept which has already been used in some of the earlier work in Markov games. I think last week Bai was talking about this Markov games, and he was also talking about this coarse correlated equilibrium concept, where we have this upper confidence bound matrix on the pairwise preferences. Let's compute the CC, or the coarse correlated equilibrium of U, which is a general sum matrix, and we can always show that for any general sum matrix, coarse correlated equilibrium always exists, and it can be solved with linear programming. So it's like polytime solvable. It's computationally efficient as well. So it just says that well, if U is the matrix of our concern, and UT is basically this upper confidence matrix. Can you come up with a PT, which is a joint distribution over the action pairs? Can you come up with a PT such that whenever the learner or the two players are playing according to this PT, the total value of the game is always greater than, no matter, if one of the player kind of deviates. It's kind of very similar to the Nash equilibrium concept, but except the fact that this is defined for more general sum matrices, for more general sum games. So that's how we compute. So we compute the upper confidence bound matrix, we compute the CCE, and we just play according to that. So we compute the CCE in polytime, and we play two arms AT/BT according to that. That CCE policy at that time. And we can show that this algorithm actually gives a optimal regret guarantee, which is square root T regret guarantee. It might not be optimal in terms of the dependency on K, but it is optimal in the dependency on T. And to show that why this gives the optimal regret guarantee, very quickly we can go over actually the results. So in fact, I mentioned that one thing to mention is that even if the underlying preference matrix is not fixed, it's changing over time, we still can get sublinear regret guarantee, square root T guarantee with this algorithm. And it will be clear from the proof why. I think I'm not making a mistake. Yes. So first key result that we can show that whenever whenever AT/BT, two arms are being played according to the CC distribution, no matter what the opponent or the benchmark is choosing, no matter whatever strategy it is taking, it need not be just a fixed I star. It can be a soft distribution over the arms. But no matter what the opponent's strategy is, the instantaneous regret of the learner is going to be something like a weighted confidence. That's just the weighted confidence intervals. And the thing is, like, if some arm AT/BT has if some arm AB, which has a very high probability, say PT/AB is quite high, then the confidence interval should be low. And if the PT/AB is low, then the confidence interval is high. But anyway, it's not incurring a lot, contributing lot in the right hand side. So once we have this result, I think it's pretty obvious from the standard bandit results that this is we can show that this is square root T, this left hand side. the trick lies in showing that why is this true. Why the instantaneous regret can be bounded with this weighted confidence intervals. And to show that this is easy, so let's just take the left half. Okay, here PTL is basically just the left marginal of PT, and PTR is the right marginal of PT. So we can show that the left arm player's regret, instantaneous regret, becomes Q transpose PLT, which is nothing but basically as if like the benchmark is playing Q, the player is playing PTL. And because we are playing from a joint distribution, that's exactly the dueling bandit regret would look like for the left player. And again, for the right player, it would look like Q transpose P, PTR. So let's just try to analyze the left half of the regret. So this quantity, and I'm just like writing it in terms of the summations, nothing else. Using Hobson's inequality, we can say that because UT or U basically, I am just dropping the notations T here. It's an upper confidence bound over P. We can show that this for all pair of arms IJ, UAB is a upper bound on PAB. So this inequality holds good. This is just some plain Hobson's inequality. And then I also changed this Q to some QT star. In fact, even if I take this pi t star to be the maximizer over all possible distributions, this is exactly equal to maximizing over a fixed arm I, because this is linear in pi t. I guess it makes sense. Like all I'm saying is maximizing over all possible distributions is same as maximizing over a fixed benchmark arm I here with respect to PTL. And then
a question.
Yes.
What was the definition of PT star here?
Where do you see PT star?
Pi t star. Pi t star.
Pi t star. Pi t star is basically just you can I can say that instead of Q, I can put here I can put max over Q belongs to delta K.
Maximizes the right hand side.
Exactly, and that maximizer is basically pi t star.
Definition.
Yes. So, and I can in the next line I have removed this pi t star and made it max over just A star, because always the maximizer would be achieved in one of the corner point of the simplex.
Sure.
So that's it. And then finally, this inequality is just because of the arm selection rule, which is the crucial point here. So because we were able to ensure that if the learner is playing from this joint distribution AB, the expected value of the game in the upper confidence sense is always more than whatever the learner could have achieved, whatever the players could have achieved. When one of the player unilaterally deviates, it's always lesser. So this comes from the CCE rule, or the arm selection rule we have, and then that's it. Basically, this is like PT UAB. Okay, so there are a few more things we need to do, because UAB is like PAB plus CAB. I have CAB here, but from the other half of the regret, like when I will be analyzing the other half, this half, I just analyze this half here. When I'll be analyzing that half, it will give another UBA. So PAB and PBA would cancel, and only PCAB would remain. Okay, so I'm not like mentioning all the details, but once we have it, we can have the similar quantity analyzed for the other half of the regret. And if we add it up, we'll get this very easily. It's not at all difficult. And once we have the desired right-hand side, probably most of you already see it, why we already have a sublinear regret guarantee, because this C, the confidence bound is like of the order of 1 by square root T. So if we just sum it over all T rounds and do some Cauchy-Schwarz trick, we get a square root T regret finally. And that's how we get a K square root T regret bound with this CCE policy. So if there is any question, I'll like to stop for a few minutes. Okay, so far, actually, I have not been even talking about the contextualization part of it. So far, I'm just talking about the best response regret, that even if we have a fixed probability matrix or fixed preference matrix or changing preference matrix, but can we actually compare against the best response benchmark? But what happens if actually this preference matrix need to be user? So what we are trying to say here is, now suppose we have user-specific contextualization in the preferences. So at time t equal to 1, t equal to 2, 3, 4, different users show up in the system, and the preference matrix PT would be a function of user context. So suppose users have some context C1, C2, CT, up to C1, C2, C3, C4, up to CT. And we say that the preference matrix is some function of this user context. So P1 is FC1, P2 is FC2. It's just some function of the user context. We as a learner definitely don't know what the function F is. So we don't know what this mapping is, but we know what the user contexts are. So now that basically makes it a contextual dueling bandit problem, that now I'm saying my preference matrix is actually okay, by the way, so I think I said something very wrong, and I didn't say it properly, but I should mention this. This particular regret algorithm, the CCE-DB regret algorithm, it works only for a fixed preference matrix. Otherwise, we can't have those confidence intervals of U, and yeah, the confidence intervals doesn't make sense. So this is only for a fixed P. This is not a changing P. We can't make it work. Otherwise, the contextual problem doesn't make sense. So now we are saying the preference matrix is changing over time. And the preference matrix is in fact a function of the underlying user context. So suppose, as I said, there is this function which maps F, which maps context to preferences, but we don't know what this function mapping is. And what we want to do is, so at every iteration, we see a context CT. We know that there is an underlying preference matrix FCT. We just don't know what FCT is. And I will just define FCT to be FT. So whenever I'm writing FT, FT is basically the preference matrix of the Tth user which is showing up in the system. Right, so here I have FT. So let's try to understand how do we define the regret in this case. Then the regret would be, so let's try to define it in the same way. We first let us assume that there is a policy class, and there is a policy. A policy is just a function from the context to the arms, exactly like contextual bandits. In the contextual bandits, we generally evaluate ourselves with respect to a fixed policy, which is a mapping from context to the actions. Here also, suppose we have a policy class pi, and we call this a policy regret, where we are trying to compare ourselves. The benchmark is the best possible policy in the hindsight. So we are playing the sequence of actions xt, yt, and when we measure the performance of the learner with respect to the policy would definitely play pi star ct. That is policy's prediction at time t, and we are playing xt. So basically, this is the relative strength of the best policy against xt. This is the relative strength of the best policy over yt, and take the average. That's the notion of policy regret. Why are we studying this policy regret? Because this has been studied once, actually back into 2015 by Dudik and some of the researchers from Microsoft Research NYC Lab. So this almost the same. They are my colleagues, so they actually introduced me to this problem. So they studied this problem for this policy regret, but they compare themselves with respect to a fixed policy, still not the best response. So now say we put this pi inside, okay? Then putting the pi inside means it again says that let's just compare every action xt, yt with respect to its best possible response, or the best benchmark. So we can again show that if we put this pi inside it, the maximizer would be just a fixed arm here. So I can just might as well maximize over a fixed arm IT star. So this is the best response regret, and we can always show that the policy regret is upper bounded by the best response regret. Because the thing is, like, actually, even if you're playing same xt yt at 2 times, because ft is changing, IT star can be different. But if you are playing if the context is same, then the pi star would give the same prediction. So definitely policy regret is a weaker notion of regret than the best response regret. So given that, the earlier results, which was on the policy regret, so this paper, which actually talked about the contextual dueling bandit paper, dueling bandit problem, but for policy regret, the two possible limitation of the work was they were able to give a regret guarantee, which is square root t, which is the optimal regret guarantee, but that was an inefficient algorithm. They were able to give another algorithm, which was follow the perturbed reader based algorithm, but it was t to the 2/3 regret. So it was suboptimal, but it was runtime efficient. So they were not able to give simultaneously a runtime efficient as well as optimal regret guarantee for contextual dueling bandits for the policy regret. What we did was we came up with a stronger notion of best response regret, and we give an optimal regret guarantee as well as runtime efficient regret guarantee for this contextual dueling bandit problem. Modulo, the only assumption we made here is that we have this is the realizability assumption. So basically, as if we know that there is a function class from which this function f is being chosen. I know the complete function class. I have the knowledge of the function class. I just don't know which the function, what the exact function is. So that's the only assumption I am making here. And for that, I am trading that. I'm able to get a simultaneously regret optimal and runtime efficient algorithm for the best response regret. So that being the contribution of main contribution of the work, let's try to understand. So this is like just a slide to explain why policy regret is weaker than best response regret, but it's kind of intuitive, so I'll not go into the details. Let's try to understand how we can try few approaches to solve this contextual dueling bandit problem, and they generally are not good enough. For example, if it's a contextual bandit algorithm, we know that exp4 gives a square root t algorithm. So if we just play the left arm and the right arm from two exp4 algorithm, which we'll call the sparring exp4 kind of technique, or just an exp4 against exp4, that gives a square root t regret algorithm for sure, but it is runtime inefficient because exp4 is runtime inefficient. So that's not a good algorithm. Maintaining a confidence interval or any sort of UCB approach doesn't also work because we just don't have a way to maintain good confidence intervals for this f for any arbitrary function class and arbitrary contexts. So UCB approaches are also not going to work very well here. What we can try to do is, if we can try to estimate f somehow, because we know the actual function class from where these functions are being generated, we can try to estimate this function f with some f hat and try to play the Nash equilibrium of f hat. Would that work? Something like this, something similar we did earlier, just that the additional step is to being able to efficiently estimate f hat. And for that, we can use some regression oracle to actually estimate this f hat function given the knowledge of the function class. Seems like that might be a good approach, but the only problem is, so if we just play simply from the Nash equilibrium, so this PT here is, by definition, PT is the Nash equilibrium distribution because it is less than or equal to 0. And I'm saying that this is for all I. So basically, no matter what I am comparing against, I'm choosing a PT which is able to make it equal to or less than or equal to 0. So PT has to be something like a Nash equilibrium policy for FT. It is still bad because I'm not exploring here. So it is possible that I can get stuck with a fixed f hat and I'll never be able to explore more choices. So I'm not being no exploration if I just play simply from the Nash equilibrium of f hat. So better option could be, I can say something like, well, it is not equal to 0, but it is maybe plus something. And I also put an exploration term here. So I ensure that if PTI is equal to 0, then this term goes to infinity. Then there is no hope that I can bound it with something finite on the right-hand side. So I put an exploration term here and I say that, well, I don't want it to be 0, but I want it to be something a little more than 0. Can that work? So let's try to understand if this approach would give us something. So we came up with the algorithm first looking at the regret expression and trying to do a min-max regret analysis of this best response regret for contextual dueling bandits. So what we try doing is, let's try to look at the learner's instantaneous regret at any fixed point t. So I will just drop this notations T here just to make sure the notations are not too complicated. And I'm just writing the inside term, the instantaneous regret of learner at any particular fixed time T here. And I'm just looking at it as a min-max game between the learner and the benchmark or the opponent. So the learner is choosing basically PT or P, and definitely he's trying to minimize the instantaneous regret. But on the other hand, the benchmark or the fixed response benchmark is trying to choose a F I star, which is really the bad I star, and also trying to choose a F, which is like a bad F, so that it can maximize it. So we are seeing it as a min-max game between the learner and the adversary, where learner is trying to minimize over P, adversary is trying to maximize over I star and F. This being the instantaneous regret of the learner at time T. Let me add another small term, subtract it with a small term, and say that can I upper bound this entire term. So I call this entire term to be the value of the game. The term that I subtract is basically the expected squared loss of the regression oracle. So I earlier mentioned that I have a regression oracle which is predicting me f hat. So if you look at this quantity, it is basically, if I'm playing, the learner is playing from P, it's just the expected squared loss, regression squared loss of the regression oracle I'm using to come up with the prediction of F. Now, the learner's instantaneous regret minus this expected square loss is what I call the value of the game. And can I actually upper bound the value of the game by a small quantity? If I can suppose do that, then I have a hope to actually get a sublinear regret guarantee, given that I have a good regression oracle. So why is that? Let me go step by step here. So first I have a min-max game over this value of the game at round T. And I just optimize it. I mean, we can just optimize it over any F, and we can just relax this PT from the joint distribution to just a product distribution. This is just some relaxations happening. There's some manipulation happening. So ultimately, if we do some manipulation, optimize over some of the quantities here, it shows up that this quantity can be upper bounded by a quantity like this. Now, this exactly looks like the Nash equilibrium term that we had earlier. And this is exactly the exploration term that we have, 1 by gamma pi sort of term. If suppose we can bound this quantity by something like k by gamma, and then we can, so because the value of the game is bounded by k by gamma, so we can say that if we take this expected squared loss on the right hand side, the instantaneous regret of the learner is bounded by k by gamma plus expected squared loss. Now, if we sum it over t rounds, we get kt by gamma plus total expected regression squared loss of the regression oracle we have times gamma. So now gamma is a tunable parameter. We can set gamma suitably, and we get a square root t regret, and multiplied by the regression squared loss performance of the regressor we have. Now, oftentimes, because it's a full information setup, we have the function class. This regression square loss, in many times, if it is a finite function class, or it is a linear class of linear predictors, class of generalized linear predictors, it can be shown that this quantity is small, in fact, logarithmic in terms of the total number of predictions or complexity of the function class. So this term being small or kind of negligible, we can say that we have a square root kt kind of regret. So what is the actual novelty in this entire analysis? To analyze this as a min-max game between the learner and the adversary, and sort of reduce this value of the game to a quantity which can be suitably upper bounded. So if we can somehow say that this particular quantity, which is same as this is bounded by k by gamma, and we can find such a p, such a distribution P, such that this quantity is upper bounded by k by gamma, we are good. We can just play from that distribution, because everything is everything is in learner's knowledge here. F hat is known, IB, everything is known here. Gamma is a tunable parameter, so we can always get a square root t regret. Modulo, we can solve this problem. But is this problem even solvable, or is there a solution exist? And we saw that actually for no matter what f hat you come up with, given this f hat satisfies the property of the zero-sum matrix games, and given this f hat satisfies a zero sum matrix games, this is basically a convex program. So firstly, this is convex in P. So it can be solved with convex programming. And the thing is, there always exists a solution. So one P has to exist always, which is the best P. So that basically says that we can always choose the strategy or basically randomize, or the XT, YT can be chosen from such a PT. And if we just come up with an algorithm which solves this convex programming at every round, then we have a good regret algorithm, and we get a square root T regret algorithm. This analysis is adapted from the SquareCB analysis of Dylan Foster and Alexander Rakhlin, which came out in 2020, which is, I think, the initial work in giving efficient algorithms for contextual multi-arm bandits, the contextual bandits. But we sort of took some ideas from the min-max analysis of this paper, and we were able to show that similar things can be worked out even for dueling bandits, given it has different notions of regret and feedback strategy. Okay, so that being the analysis, now the algorithm is easy to understand. So the algorithm basically says that, initially we can just randomly explore a bit. No matter what, whatever data we have, come up with a regression estimate of the regression function f. So use a regression oracle, or it can be like least square regression or whatever favorite regression oracle we have, and come up with an estimate of f hat, and solve this convex programming problem, which is efficiently solvable because it's convex in P, and there is always exist a solution for all such f hat. So come up with, solve it, and play according to that distribution. And that essentially gives us the square root T regret for square root T times the regression squared loss kind of regret for dueling bandits. And this is also optimal. I mean, given this regression loss is kind of logarithmic in T, logarithmic in terms of the function class, or it's not too huge depending on the complexity of the function class. We have a square root T algorithm, which is optimal, because EXP4, which is an inefficient algorithm, that also get a square root T algorithm, and we can, lower bound wise, we can always analyze that it is square root. Even like contextual bandits has a square root T regret, and dueling bandit being a harder setup than contextual bandits, contextual dueling bandit being a harder setup than that, order square root T is the optimal we can hope for. So just to summarize here, we just discussed the problem of dueling bandit. We have come up with this notion of stronger benchmark, which is the fixed response benchmark for dueling bandits. And we show that just for fixed preference matrices, if the preference matrix is fixed, how to get a sublinear square root T algorithm for standard dueling bandits against fixed best response regret. Now coming to the contextual setting, can we actually come up with a generalization of this algorithm which works for contextual dueling bandit and still gives square root T algorithm for for best response regret? And we are actually able to give such an algorithm which is optimal and efficient through min-max regret analysis that we just saw. This is tied modulo. We have a reasonable function class and a good regressor oracle. So in future, I think we have been only dealing with finite action spaces, so we can try to work with that. We were dealing with some online regression problems, so we can try to see if we can make it work with some offline regression oracle, or extend it to subset-wise models instead of dueling models. And there are like many exciting works that can be done. Even reducing the contextual dueling bandit to contextual contextual bandit problem, that can be an interesting thing if we can reduce the problem to some multi-arm bandit problem and just solve the multi-arm bandit problem. So there are a few interesting directions we can work on. But yeah, that's it. So thanks a lot. If you have questions, please let us know. And I hope like there might be questions from the analysis. I'll be happy to clarify those.
All right, thank you very much. So, so I don't know if there are any questions remaining. So there was a question by Francesco Tanini during the talk. I don't know if that has been clarified in the meantime. Francesco, maybe you can ask a question now. Just go ahead and unmute yourself if you're here.
Okay. Hi, a short question about, so at the beginning regarding the non-contextual stuff, actually. So I'm taking it quite a lot. For the best response regret, you had a square root of t dependence in the regret, right? Which is maybe expected. Is that optimal, or could you show that that is optimal for the best response thing in the non-contextual case?
Yes, it is optimal because even the fixed benchmark regret, which is a weaker notion than the best response regret, the fixed benchmark regret, I mean, I can come up with problem instances. I mean, it is definitely not an instant dependent guarantee. I'm not making it dependent on the any notion of gap here. But in the worst case, gap independent regret guarantee wise, square root t is the best we can hope for.
Okay, but instance dependent, it may be possible to get logarithmic.
Definitely.
Also for the best response regret, you think so, or? Because I'm curious between the gap, right, between best response regret and if you have the max in front of the summation, that seems. I'm not sure how big the difference is.
I just don't know what the definition of gap would be actually in that case, because the best response benchmark is very much a function of the entire sequence xtyt, or in fact, it is not even a function of xtyt, it is a function of xtyt at every round, the player against we are comparing with, the benchmark against we are comparing with. So the notion of gap, like we can appropriately think of a notion of gap. I mean, maybe like ITs.
Relating it to so where I'm coming from is matrix games with bandit feedback, which would be just a slightly more general problem, right? Where you don't have this preference matrix, but you have just a general matrix, and you see bandit feedback, and then problem dependence could, for example, come in as a distance to the value of the game, right? Which kind of describes how difficult it is, maybe.
I see. Got it.
Yeah, just curious about your opinion on that.
I see. So yeah, that might be interesting. Distance from the value of the game. I need to understand what exactly that boils down to for the dueling bandit setup, or what exactly the value distance from the value.
The value would actually be 0, right?
Would be
for the dueling bandit matrix, right? For the matrix, I mean, it's a symmetric game, right? For the two players who choose the arms.
But
so
what would be the distance of the fixed bench, I mean the strongest benchmark or the best response benchmark?
Yeah, the distance to 1/2 then, right? The probability, if you have some arm I has a probability of say 0.7 to win against arm J, I would say that the distance is then 0.2, right?
Okay.
But that might actually not make a lot of sense.
Yeah, that way. Yeah, exactly. So defining the distance with respect, I mean, in terms of the preferences.
I'm myself not very sure that the distance makes sense.
But that makes sense actually. I mean, how to define it. Generally, the gap is defined in terms of the preferences for dueling bandit, so that makes perfect sense.
Because it should definitely make it easier, right? If you have, depending on the gaps, right?
Yes. Yeah. So there can be definitely, like, for example, if there is a preference matrix which is like just the first entry is all 1 and rest of the entries are like all 0s. Yeah. It's a very easy preference matrix, and I mean I can probably learn it just playing it 3 times. Yeah, that's it. So
okay, maybe another follow-up. So to ask so So did you assume a Condorcet winner for the non-contextual stuff?
No, because we just saying like it is the best response regret. So the preference matrix do not have Condorcet winner or any such.
Okay, and then another. How does your result relate to the von Neumann winner then? And maybe as the background, the von Neumann winner is the distribution over arms, which beats any other arm. So
good question. Yeah, it is actually stronger than even the von Neumann winner. So suppose because we are comparing against the fixed the best response. So if xt and yt suppose is the von Neumann distribution, then we can say that the best response exactly is the von Neumann distribution, because the opponent's best. But if xt is yt is like something weird, initially I can play something weird. Maybe the von Neumann distribution is not the one which is beating me the most. For example, giving you a simple example. Okay, suppose Condorcet winner is there. Okay, and there is like the Condorcet winner is beating every other arm with probability 0.51. But it's still a Condorcet winner. So the von Neumann distribution is basically one hot vector which has mass 1 in the converts to winner and rest of the thing as 0. Do you agree that is the one Nash equilibrium?
Yeah.
But the thing is, like, suppose I am playing arm 3 and arm 3 is getting badly bitten by arm 2. So say arm 2 beats arm 3 with probability 0.99. And I am playing arm 3 and 4, both are getting badly bitten by arm 2, which is with 0.99. But so my best response is still not von Neumann.
Yeah,
but
so essentially when you have a messy preference, slightly messy preference matrix, right?
Yeah.
If you would have like a utility-based setting, that could not happen, right? But
right, exactly.
Okay.
Exactly, it's not utility, it's more general than utility. Yeah, right.
Okay, thanks.
Yeah, that's nice questions. Thanks a lot. Other questions?
I can jump in. I do have a clarification question.
Yes.
For also this first part.
Okay.
If you go to the algorithm,
the first algorithm.
Response regret. Yeah, it's like page 15 or something.
Right. Sorry.
Why we saw the animation? It's okay.
Yeah, it's just taking a bit too time to move.
That's fine. The animations. Almost there.
Okay, it's almost there.
Yeah, this one.
Yes.
So I'm looking at this coarse correlated equilibrium, and I noticed that something unexpected is going on. To me, what's unexpected is that we have these two inequalities, right?
Yes.
And normally you have this joint distribution that you're playing, and then there is a payoff for one of the players and wants to maximize its payoff.
Yes.
And then deviation from this distribution, as long as the margin of the other distribution is capped, is not going to give a value increase. So that's, and then you do the same for the second player with the payoff. So that's the definition I do remember. But here what is happening is that the order of arguments are flipped in the second equation. It's like PTAB times UTBA. And so it's like, okay, what is that? So what are we doing here?
So,
so what is really the payoff for the A player? What is the payoff for the B player? Is this really coarse correlated equilibrium? How do I map this to what I understand as coarse correlated equilibrium?
So actually, I would say, So firstly, I will try to probably write a better notion of this, which will make it a little more clear. So you, let me see if I can write anywhere here, or I have a better frame to write. Let me clear the frame here. Erase. Okay. So so by definition, if we said that our UAB is just like something, our P hat AB, which is our estimated preference, plus CAB. That's how U is defined, right? So I can define a lower confidence bound, which is P hat AB minus CAB. And one thing for sure is UAB is equal to minus of LBA because of the antisymmetry nature of these preferences, okay? Now the thing is, let's just try to write down whatever I have written in a slightly different way. That would make more sense. For the first player is trying to maximize the value. So the first player is trying to maximize the regret, and the second player is trying to minimize the regret. Okay, so one player tries to, so it's a zero-sum game. So first player is as if trying to come up with a PT. So
I guess so you're gonna say that the payoff for the second player, the B player, is L, and
exactly.
the payoff for the first player is U, and if you plug that in, then everything works out.
Exactly. So here I want that whenever I'm playing from this joint distribution, the lower confidence, because the second player would try to actually like minimize the lower confidence bound in some sense. I mean, it tries to minimize the game. So for the second player, this is exactly what we want. So minimum over B, then we can say this is A is being drawn from this the left marginal, whatever the marginal is.
Just write PA.
Just write PA, okay? So PA, so PAI, and I from 1 to K. And this is IB. So minimize over B star, whatever, minimize over all possible arms.
You also multiply with LAB?
I'm sorry. This is
LIB?
LIB.
But there is a P as well. Okay, so there is a marginal, there is L, like
sorry.
It's a product.
Sorry, very sorry. Okay. Just let me make it expectation. It will be clear. Yeah. So expectation, the first player is playing from PA or P.
That's
PA.
good. That's good.
Okay.
That's good.
So L A B. And B star is just minimize overall possible arms in the arm space.
Good.
And so this is what I want. And now you make this to be minus of UBA. You will get that. Okay. So, and this is how actually we get this coarse correlated equilibrium definition. I mean, actually, we read this definition U-Bai's paper where they have this upper confidence bound on the reward matrix. I mean, they call it U.
I tried to do this, but I don't get the second equation exactly. I get some variables flipped because you have PAB times UBA. And like, if I take the negative of the whole thing, then I would get UAB, like on the left-hand side.
No, but here I have AB, right? That's why I got BA. So where is it?
So
here.
whatever you wrote, you multiply it by minus 1.
This is AB. This is AB, right?
That's right. That's right. And then somehow it becomes BA.
Yes, because UAB is minus of ULABA. You are missing that. Oh, it's anti-symmetric. That's why.
Oh, it's mine. Oh.
Because PIJ is 1 minus PJI.
Right, right. Okay.
PIJ is
that's what
minus of PJI.
Okay. Yeah. Okay. Good.
Right.
That explains it. All right. Sorry about that. Okay. Makes sense.
Yeah. Probably I should have written it the other way around, and that would have introduced too many notations.
Okay.
That's the reason.
Okay. Can I ask also something about that again? Because
yes.
I tried a similar algorithm for a different problem. And why are you choosing the coarse correlated equilibrium and not just the general sum game of the upper and lower confidence bounds you have there?
Oh no, I didn't.
You define the upper confidence bound matrix and the lower confidence bound matrix, right? And intuitively, yes. I would say play a Nash equilibrium of this general sum game, which is
exactly
by this. Why not?
you mean the Nash equilibrium of the general sum game?
Yeah,
but we have. Why would the Nash equilibrium exist even? Like Nash equilibrium did not exist. Nash equilibrium would exist for the general sum game, but it might be computationally inefficient.
Okay, and all the properties are guaranteed by the coarse correlated equilibrium that you
whatever need. Properties we need to prove the regret guarantee, that is ensured and it is efficiently solvable.
Okay, fair enough. Yeah. Thanks.
Yeah, thanks for the question. Yeah.
So then regarding the second algorithm for the contextual settings.
Yes.
So maybe I missed that, but is it also using this reduction to zero-sum games? It didn't seem that way to me.
It is using some property that FT is basically the zero-sum matrix here, because FT is basically what I call as F of CT in the context. It is the zero-sum. It has the zero-sum property. We are using it somewhere in the analysis, but I'm not using something like a coarse correlated equilibrium of something like that.
Not doing any equilibrium computation.
Yes, but the thing is, I would say still something which is more intuitive, not coming out very clearly the way I discussed it. I mean, I should have been more. So if you just look at this quantity here, right, the first quantity, and don't look at the second quantity that I have written. Okay. So this is how I'm choosing my PT, from where I'm going to play my arms. So if you look at the first quantity, as if like FT, assuming that FT hat is my true preference matrix, if there is a PT which ensures that this FT hat IB, PTB, so this is less than 0 for all choices of I, this PT has to be like the Nash equilibrium distribution of FT. Because for all I, we are ensuring this is going to happen. So if FT is any valid preference matrix or a zero-sum matrix, for PT to have this property, it is the Nash equilibrium policy of FT. But I'm not saying this is less than 0 because as I said, like I have to be explorative also. I have to do some exploration. So I'm adding this term as if like we are not coming up with this term. We came up with all this update rule from that analysis. But after we came up with that update rule, I am trying to parse it in this way. So PT is close to the Nash equilibrium, modulo the fact that it should also have some bit of exploration. So 1 by gamma PTI is just ensuring that we put at least some weight in every component PTI so that we never stop exploring any of it. And then we can't say this is going to be less than 0. That is not possible because this is already a positive quantity. So we say that this is K by gamma. That is like the bare minimum we can tolerate. And if we can tolerate up to K by gamma, we are still good. So that's how it's kind of a combination of the Nash equilibrium, but with some exploration.
Right. Yeah, that makes perfect sense. But then on the previous slide, we had like a slightly different presentation of this method where you framed it
this
as,
one, right? It's.
Well, you said that it is a convex program. I'm just trying to see this.
It's the same thing. Here I have written the same thing. If you look at it. The only thing I have not made very clear is there is a PK here, and what is this PK doing? I should not have put this PK because some do over K equal to 1 to K, PK is equal to 1. So that is not there. So this expression is exactly equal to this expression. I mean, I have not explained the steps, how from here I came to this step. I have not explained those. That requires some optimization over F hat, some relaxations or some other things. I didn't explain those intermediate steps. But when I just tried, we just tried making this back calculation that this is our instantaneous regret. If we make it a slightly lesser, just subtract it by the expected squared loss, and can we upper bound it by something like small K by gamma? Then we can take the squared loss on the other side and we can get this. As long as we have this, we have a square root guarantee. So all we tried doing was try to bound this value of the game by K by gamma. And we derived this exact expression, this combination of Nash equilibrium plus exploration, that kind of expression. We got it from this analysis. This is exactly the same expression I have written in the next page. Maybe it is not obvious, but it's kind of the same expression. This too is the same expressions.
Yeah, and I also get this idea of subtracting this squared prediction error. So this is what sort of comes from the SquareCB.
SquareCB analysis, exactly. That's true.
Yeah, but so in the case of SquareCB, I guess there's like a closed form solution for this.
Exactly. That's also one of the very much, I tried so much to come up with that's also I was mentioning in the future work that if we can like somehow reduce it to two SquareCB competing with each other or something like that, we have a closed form expression instead of solving this common convex programming every round. That would be great. But I have tried, not too hard, but I have tried, but couldn't succeed. Yeah, I mean, not any success still.
Well, you don't necessarily need like the exact optimizer of this, right? I guess some relaxation that gets within a constant factor should be enough. No?
Not exactly this, the closed form of this. I mean, yeah, I don't think a closed form of this we can come up with. I tried like come up with another closed form solution which might work as you're saying, but not any success till now. Just another algorithm which might have some closed form expression for PT updates, but didn't get anything so far.
Yeah, I guess. I think that would be very interesting.
Yeah, that would be interesting for sure.
So can I have a question that connects the second and the first part back? So we could try to apply this second part algorithm for the first part.
Yes,
where you have a fixed matrix, and you would get the square root KT guarantee up log, right?
Yes.
And this algorithm, the way it works is that it just estimate empirically the entries of the symmetrized or anti-symmetric matrix, the PT or the matrix.
Exactly.
And then it would compute this exploration distribution in line 6. And
exactly.
So when you're saying that line 7, sample XT, YT from PT, I said that PT was just over the simplex.
Exactly. It is also
product.
Yeah. It is a product distribution. So
Okay.
here I am saying I'm relaxing. I started with the joint, but I relaxed.
No.
It still works.
It's just a clarification question that like,
yes.
So you mean that like both XT and YT are independent chosen
exactly.
PD.
Exactly. Okay. It still works. Yeah. Earlier case, actually, CCE has to be a joint distribution. I mean, I didn't see actually if we can always claim that the CCE distribution that we are getting at every round can be a product distribution. I at least didn't see it. But here we have a product distribution. And this algorithm definitely works for the standard dueling bandit setup as well. The only thing why I explained that algorithm is because it has some connection with this Markov game literature.
Yeah.
So maybe if we try to generalize it to the RL setup, that might be useful. Yeah.
Okay. Which one do you think is a better algorithm for the simple setting?
You can answer this off the record if you want. Not necessarily. You can have your favorite. It's okay.
No. I mean, so I have like a correct answer here because the second algorithm already gives like a better rate because it's square root kt, whereas the first algorithm gives k square root t. So definitely.
Why is that? Okay. And is that an artifact of the analysis of the first algorithm, or is it coming from the algorithm itself?
It could be the artifact because I mean, so when we when we take the cautious, could be the artifact of the analysis, but I don't know if that square root thing can be shaved off. Let me see if I can just go back easily. So you still see the screen, right? Yes. So all I'm saying here is we get this PTAB CAB, right? Now you see the summation is actually over k square quantities. So we get square root of k square. So when you do the usual standard stuff to bound this quantity, we get square root over k square. And that becomes k square root t.
So now wait for a second. Like, how can you even get the square root kt bound? So what's the explanation for that?
We get the square root kt. Why do
we get? You have k squared entries to estimate. Okay, k squared over 2, but.
Yeah, but actually the action space for the opponent and the action space of the learner both is order k. So if you look at that way, so the action space
is not possible. Yeah, you are only looking for one row which is good, which is like k different choices, even though that there are k squared entries.
Yeah, there are k squared entries.
And somehow you can be clever about this. But it's a whole row. It's a property of the whole row. It has to be good row.
It has to be, but I mean, I am also not saying I am always comparing with respect to a fixed row or something, or it's the whole row is good. I can even allow in benchmark, which is a joint.
Sure, which is even harder.
Yeah. But the action space at any point of time, the action space of the opponent and the action space of the learner, it is order k. So I have only k items. of course, you are having to choose k-square items every round. That's the nature of the dueling game. I mean, for example, I can also say you that it's a subset-wise game now, and you can choose q items every round. Then you have to choose k to the q. It becomes like k to the q. We definitely don't want something like square root of k to the q or something. We know that because the decision space is still order k. It is this is the artifact of how the problem is defined, that you are having to choose two pair of actions or q items at the same time. But that should not blow up the decision complexity in the decision space. Does that make sense? Because I am not comparing myself with respect to something like a k-square complex opponent. I'm comparing myself with respect to a k opponent.
Okay. Interesting.
In fact, I mean, even if you look at the dueling bandit literature for contorsive winner, that simple contorsive winner thing, we have a dependency. Even it is a gap-dependent guarantee, we have like k log t by delta kind of bound, where delta is a preference-dependent gap, but it's order k. So, and for contorsive winner, it's easier to see because all we...
Ouch. Uh-oh. Wait, did we lose Aadirupa?
Thought it was just me again. My internet's been crashing.
But the internet is now really having issues.
Our internet is fine.
Seems so.
Okay. Let's hope that she comes back. You can't finish the sentence.
Want is the good item, one good item against which we compare.
Oh, sorry, Aadirupa, we lost you for several seconds, maybe even minutes.
Oh, okay. I don't think I said anything. I mean, I was just mostly saying this contorsive winner thing and said that this order k dependency is much more acceptable. If we think that the preference matrix has contorsive winner, then it is much more acceptable. We can directly see. But even otherwise, it is a general preference matrix.
Okay.
What we compare against is always k number of items. That is the complexity of our decision space. And how we change the problem setup, what you can choose should not affect the complexity of the decision space. I mean, that should not blow up.
Okay. All right. Thank you.
Yeah. Okay. So that's it.
Okay.
Thanks a lot for the nice questions.
This was great. Thank you again.
Thanks a lot. Thanks
very much.
Yes,
Thanks,
thank
Chiara.
you so much.
Thanks, Java. Thanks, everyone.